so we are continuing where we left off from last time. We are going to start by writing the electron configuration for sulfur. So first thing we're going to do is find sulfur on our periodic table. So on the periodic table, where is sulfur? So sulfur is S. Good. It is what atomic number? 16. And what block of our periodic table is it in? It's in our P block, yeah. So this is our P block. So sulfur is right here in our P block, okay? So like I said, reading the periodic table like a book, we always start up here, and then we just go across all the way until we hit it. So everything we pass through, we have to write down. Sulfur, though, okay, so it's in our P block. What energy level? Yeah, so 3. So this is 3P. And then it's going to be 3P what? 4. So you figure out your little superscript number just by counting. So 1, 2, 3, 4. So this is 3P4. 3P4 is going to be the very last thing that we write down. But all of the other sublevels and energy levels that we pass through to get to 3P4, we also have to write down. So we always start with 1S. Okay? And every energy level and every sublevel that we pass through is going to be full because they fill from lowest energy to highest energy, and we write them in that order. Okay? So everything up until 3P4 is going to be full. So for 1S to be full, how many electrons would there be? 2. So we would write 1S2. If you remember, an S sublevel has how many orbitals? 1 orbital, and each orbital can hold how many electrons? 2. So an S sublevel is only ever going to have a maximum of 2 electrons. Okay, so we started here, we got through the 1S. Now we hit here. Sulfur is not in our 2S, so that's going to be full. So we're going to write 2S, 2. Reading the periodic table like a book. Next we hit 2P. Sulfur is not in 2P, so we're going to write 2P. And then how many electrons are there going to be? 6. So it's going to be 2P6. If you forgot, P has 3 orbitals. Each orbital can hold 2 electrons, so 6 total. And even if you forget that, our periodic table is arranged so that all you have to do is count. 1, 2, 3, 4, 5, 6. So 6 elements in this P block on the periodic table, there can be 6 electrons. So we did 2P, now we're down here, 3S. Sulfur is not in our 3S, so 3S is full, so it's going to be 3S what? 2. And then what did I say the last thing we were going to write was? 3P4. So once we get to the 3P, we're going to write our 3P4, and that's where we stop. This is the electron configuration for sulfur. Questions? Okay. So now we're going to do our orbital diagram. So our orbital diagram was this thing with the boxes here, okay? But instead of writing them like up, increasing this way, we're just going to write them from left to right, okay? So remember, each of the boxes represents an orbital. So we said how many orbitals does an S have? 1, so we're going to draw 1 box, and we're going to label it 1S. Then we're going to hit 2S. How many boxes would we draw? We're just going to draw 1, because it's still an S sublevel. It's just, all it's saying is it's this S sublevel on this second energy level. So there's still only 1 box, 1 orbital. We're just going to label it 2S. Next we hit 2P. How many orbitals for a P? 3. So how many boxes? 3. So what I like to do is I like to draw this kind of long rectangle and then break it up into 3. However, if you just want to draw a box and then keep drawing boxes all off of it, you totally can. I just like to group them together because whenever I go and grade it, this tells me that you know that all of these are 2P, and your spacing isn't weird to where I think that you have 2 boxes for 2s. Okay, so by grouping them together, this tells me that you know that there are 3 boxes for 2p. Okay, after 2p is what? 3s, so just 1 box. And then we hit 3p4, so how many boxes here? How many orbitals does p have? 3. So we're going to draw 3 boxes. So no matter what, no matter how many electrons there are, if we have any electrons in that sublevel, we draw all of the boxes for all the orbitals, even if we're not going to put any electrons in those boxes. Okay, so now we're going to go and fill them. So what off-bow said that we have to fill lowest energy to highest energy. So we start with our 1s. We have to completely fill 1s before we move on to 2s. Okay? Now, this little number here, this tells you how many electrons are going to be in that sublevel. So how many electrons are there going to be in the 1s? 2. Do you remember how we represent those electrons in the boxes? With arrows. Okay? Another dude, Pauli, so the Pauli exclusion principle, said that our arrows had to be what? Can we have 2 up arrows? Are they going to be 2 up, 2 down, opposite directions? Opposite directions. So Pauli said that we have to have our electrons have to be going in opposite directions. So we cannot have 2 up arrows, 2 down arrows. If we have 2 arrows in the same box, they have to be going in opposite directions. So we are going to have 2 arrows in this box, so we're going to draw an up arrow and a down arrow. Now I do these little half arrows here. Feel free to use like full arrows. This is just kind of like my habits. It makes it go faster and it saves me space. So if you want to do these half arrows, by all means, you're welcome to. If you want to keep full arrows, you can. But these are arrows. This is not like a 1. Okay. So then we're going to get to 2s. How many electrons are going to be in the 2s? 2. So we can go 1 up, 1 down. Next we hit 2p. How many electrons are there going to be? 6. Now we get to Hund. Hund's rule. Do y'all remember what Hund's rule said? What did Hund's rule say? One in each box before you double. So what that means is that we hit 2p. These have 3 boxes. So we would have to have 1 electron in each box before we can go back and double up. Okay? I like to kind of think of this as kind of like a dinner party. Okay? So we only have I only made a certain amount of food. We only have a certain number of electrons. Okay? I want to make sure that everyone has the chance to get 1 serving before someone goes back and gets extras, gets a second serving, okay? So all of our boxes deserve to have 1 electron before 1 box gets 2. Yes? Okay. So now we get to 3s. How many electrons? 2, so we'll have 2 arrows. Now we get to 3p. How many electrons? 4. So what is this going to look like? Good. So we're going to have 2 boxes have just 1 up arrow, and then our first box is going to also have a down arrow. Yes? We always want to start with the first box. Yeah, so they asked, does it matter which box you put our down arrow in? We also want to start going left to right, and so whenever we hit the end, we're going to go back and put start from the first one as well. Yeah. Good question. Anyone else? All right. So the next thing asks, what are the highest energy amount electrons? Okay. So Our highest energy amount electrons are the ones that we wrote last, because we said we fill from lowest to highest energy. So what, in our electron configuration, what did we write last? 3p4. So 3p4, these are our highest energy amount electrons. Now, talking about valence. Valence electrons mean they're on our outermost energy level, okay? Looking here, what tells us what energy level our electrons are on? What part of this tells us what energy level our electrons are on? Our big front numbers. So like this 1, this 2, this 3, that tells us our energy level. Okay, so we're going to look for the electrons that have the largest first number. So what would that be? It'd be 3. So anything with an energy level of 3 would be our valence electron. So that would be our 3s2 and 3p4. Both of those are considered valence. All right. So then how many total valence do we have? 6. We have total 6 valence electrons. 4 plus 2 is 6. All right, looking at our orbital diagram, how many unpaired do we have? 2. We have 2 arrows that don't have a buddy, so we've got 2 unpaired electrons. Okay, so this here, it's okay if you don't know this. We're about to go over it in just a second. I just want to do this one with you first. So this says, what is the most likely ion for sulfur? As a reminder, ions are whenever we gain or lose electrons. Okay? The goal of all of our elements is to have a full valence shell. So they either want to gain electrons to get to 8, or they want to lose electrons to get down to 0. So the energy level below has a full shell. Okay? So looking at sulfur, do you think it's going to want to lose or gain electrons? So want to lose to get down to 0 or gain to get up to 8? What do you think is going to be easier? Gain, right? Because it's at 6. It's going to be easier to gain to get to 8 than to lose all of these to get down to 0. Okay, so how many does it want to gain? 2. So it's going to want to gain 2 electrons. So what does that look like for the ion? What is its charge going to be? It's going to be an anion because it's gaining electrons. So how many did it gain? 2. So is it going to be plus 2 or negative 2? Negative 2. Okay, so if it gained 2 electrons, what's going to be the new configuration? What changes? So if it's gaining 2 electrons, what does the new configuration look like? What's the only thing that changes? Yeah, our 3p4 is going to change to 3p6 because we gained 2. So everything else is the same. So it's still 1s2, 2s2, 2p6, 3s2, but now instead of 3p4, it's 3p6 because we gained 2 electrons. Okay, so if we're gaining 2 electrons, do you think our new ion, is it going to be bigger or smaller than the original atom? Bigger. It's going to be larger. We gained 2 electrons. It's going to be a bit bigger. Okay, now this last question. It asks, with which noble gas is the sulfur ion isoelectronic? Isoelectronic means same electron configuration. So iso means same. Electronic is referring to electrons. So with this new configuration of 1s2, 2s2, 2p6, 3s2, 3p6, what noble gas has the exact same electron configuration as this? It's going to be argon. Argon is in the 3p6 spot. So it's argon's noble gas, or argon's electron configuration is going to end in 3p6. So the sulfur ion is isoelectronic with argon. It has the same electron configuration. Okay, so the ion thing might be a little tricky. We haven't really gone into that before. So what we're going to do now is we're actually going to talk about it. So flip to the next page. We'll come back and do strontium in a second. But we're going to talk about what it means when forming ions. Okay. So, to form ions, our atoms are either going to gain or lose electrons. Let's talk about metals. Where are the metals on the periodic table? Where? Yeah, they're kind of more on the left side, right? So, like, let's take a look. Like, we know group 1 are alkaline metals, group 2 are alkaline earth metals, right? We know these are metals. How many valence electrons do our group 1s have? 1. They're going to have 1 valence electron. So, do you think they're going to want to lose or gain electrons? They're going to want to lose. They've only got 1. So, it's going to be a lot easier for them to lose 1 electron than to gain 7, right? So all of our metals, so most of our metals are going to lose electrons in order to become isoelectronic, that word again. To become isoelectronic with the nearest noble gas. Whenever our metals lose electrons, do you think it's going to be smaller or larger than the original? Smaller. So then let's think about our nonmetals. Our nonmetals are where? They're on the right over here. They have a much higher number of valence electrons. Like sulfur, for example, sulfur, right, had 6. We decided that for sulfur, it was going to be easier for it to gain 2 than to lose all 6. That's the same for our nonmetals. Our nonmetals are going to what? Gain. They're going to gain electrons in order to become isoelectronic with the nearest noble gas. So whenever they gain electrons, what do you think is going to happen to the size? Good. It's going to be larger. Okay, now these elements do that because, like I said before, the goal of all of our elements, all of our atoms, is to be like a noble gas. Noble gases have a full valence shell. They have 8 valence electrons. That's why noble gases don't react. So you learned last unit that noble gases don't react with other elements. And we learned that alkali metals and halogens react they're very reactive. It's because our alkali and our halogens they're only 1 valence electron away from having a full shell. Either they need to gain 1 or just lose 1. Okay? Our noble gases aren't reactive because they're already at 8. They're happy. They don't want to change their number of electrons. So all of our elements are trying to get like a noble gas. Okay, so let's take a look here. We're going to fill out this table. So group 1. So talking about the electron configuration for these of our valence electrons. Looking at group 1, how would we end our electron configuration if our element was in group 1? What would be the last thing we write? S1. Yeah. The last thing we would write would be S1. What about those in group 2? S2. Good. Group 13. What would that be? So group 13 is right here. that would be P1. However, is just P1 our valence electrons? No, it's also our S. So for 13, our valence electrons, that would be S2, P1. I'm not writing the energy level because that's going to change based on what period the element is we're talking about. Okay, this is just how it, ignoring energy level, they always look like this. Okay, looking at our group 15 nonmetals, okay, group 15, what would its electron configuration be for the valence? S2, P what? P3. What about 16? S2, P4. And group 17? S2, P5. Good. We're not writing group 18 because they are, they're not going to change. They're always going to be, they don't want to lose or gain any electrons. Okay, so then group 1, how many valence electrons does it have? 1. What about group 2? 2. Group 13 has 3. 2 plus 1 is 3. Group 15, 16, 17, 7. And I'll teach you a little trick too. 17, the last number, 7, 7 valence electrons. 16, last number, 6, 6 valence electrons. Okay, so then do you think group 1 is going to want to lose or gain electrons? Lose. How many is it going to lose? It's going to lose 1. What about group 2? It's going to lose 2. Group 13? It's going to lose 3. So now we're talking about the group 15 non-metals. They're going to gain how many? Good. They're going to gain 3. Because remember, we want to get to 8. So if they've got 5, they're 3 away. Group 16, what are they going to do? They're going to gain 2. And what about 17? Gain 1. Okay. So let's think about what that charge is. So remember, whenever we lose electrons, what's happening to our charge? It becomes positive, right? Because electrons are negative, so minus a negative is a positive. One way sometimes I like to think about it that helps you remember, so I like to think of electrons as like negative people in our life, okay? Whenever we lose, whenever we get rid of those negative people in our life, what happens? Yeah, it gets better. We get more positive, right? That's what our charge is. Whenever we're gaining negative people, what happens? What happens? We get negative. Okay, so that's what's happening to our charge. Okay, so if we're losing an electron, is that going to be positive or negative? Positive. Positive what? 1. Okay, what would be the charge for group 2? Positive 2. Group 13. Positive 3. What about group 15? Negative 3. Good, because we're gaining now. Group 16. Negative 2. Group 17. Negative 1. Okay, so then if we're losing electrons, is it going to be smaller or larger than the original? Smaller. About group 2. Smaller. Group 3, 13. Smaller. Group 15. Larger, because now we're gaining. 16. Larger. And group 17. Larger. Okay. So do we kind of understand what's happening for these ions now? Yes, question. That's why we didn't talk about it. So we're not going to, so someone asked, like, what happens if we're in, like, group 14 and we've got 4 valence electrons because it's smack dab in the middle? what's going to happen is it would depend on whether it's a metal or a non-metal. Our metals are going to lose, our non-metals are going to gain, but we've got some like special things that happen that we're not going to talk about right now, which is kind of why we skipped group 14. So we're not going to ask you about group 14 right now. Okay, so what I want y'all to do is go back, and now I want you to do strontium. So do this strontium example on page 14 all by yourself. Okay, so go ahead and pause the video, and then whenever you're ready to check your answers, come back. Okay, so here is the key. So the electron configuration for strontium should be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. So strontium is in the 5s2 position, so that is the last one that we're going to write. Then we went through and did our orbital diagrams, okay? So for every s, it got 1 box, every p, we had 3, and then the d's had 5. So each of these sublevels was completely full. So that means that every single box had 2 arrows in it. Okay. So then our highest energy amount of electrons, those are the ones we wrote last, so that would be 5s2. Our valence electrons are the ones in the highest energy level. Those would also be our 5s2 electrons because it's the one with the largest number in front, 5. And we've got 2 of them. Now, unpaired electrons, we look at our orbital diagram. Strontium has 0. None of these electrons, none of these arrows are missing a buddy. All of them have a pair. Okay, our most likely ion for strontium. So we're going to go and look at the valence electrons. Unpaired electrons don't really have anything to do with the ion. Okay, it matters with the valence. So strontium had 2 valence, which means it's going, and strontium is a metal, which means it's going to want to lose electrons. It's going to lose those 2 valence to become strontium plus 2. Meaning the new electron configuration is the same as before, but getting rid of the 5s2. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Yes? Nope, you gotta fill all of them. Yep, you gotta fill all of them. So for the orbital diagram, you gotta fill all of them.
Are we ever gonna have one that's like
Down there, probably not. So we might make you write the electron configuration for something like in the 6th energy level, but we won't make you draw the orbital diagram for something like that. Okay. Yeah, SR plus 2. All right. Shh. Okay. So this ion would be smaller because we lost electrons, and then it's isoelectronic with krypton. So it would not be xenon, okay? It lost 2 electrons. So we go to the noble gas that came before it. Okay, so we look for the noble gas that is in the 4p6 position. That would be krypton. All right, questions? We okay? All right, so now let's talk about Bohr diagram. Okay, so if I can find what I did with my pen. Okay. Alright, so what we're going to do here is we're going to start off by doing the same. We're going to write our electron configuration, write our orbital diagram, okay, but then we're going to place those electrons on our Bohr diagram. Okay, so first thing we're going to identify is this isotope, aluminum-27 with no charge, an atom or an ion? It's an atom. How do we know it's an atom? Has no charge. Perfect. Okay, the nuclear symbol for aluminum is going to look like what? Al. It's in the upper left. Upper left is what? 27. What is that 27? The mass. Where did we get it from? It was given. It's this aluminum-27. Remember, this 27 is the mass. So 27, and then what goes in the bottom left? 13, which is what? The atomic number. Okay, so then how many protons does aluminum have? 13. How many neutrons? 14. How many electrons? 13. Okay, so then we're going to write the electron configuration. Aluminum is in what spot? So aluminum's right here. Yeah. All right, so aluminum is in what spot? 3p what? 3p1. So that means everything before 3p1 is going to be full. So 1s2, 2s2, 2p6, 3s2, and then we've got 3p1. Because we pass through everything until we get to 3p1. Okay, so now we're going to draw our orbital diagram. So our 1s, 2s, 2p, 3s, and then how many boxes are we going to draw for this 3p? 3. Good. We're drawing all of our boxes. Just because there's only one electron does not mean that we're drawing one box. We draw all of them. Okay, so 3p is our last box, so that means everything before 3p is going to be full, so we can go ahead and fill it in. Okay, and then how many arrows are going to be in this 3p? 1. So we're just going to put 1 up arrow in this first box. Yes? Doesn't have to be. As long as it's only 1 arrow, doesn't really matter the direction. However, all of them have to be the same direction. So like if we were to go on, if you were to draw down arrow here, these would have to be down arrows as well. In the same box, yeah. So in the same box, we have to have 1 up and 1 down. We can't have 2 down or 2 up. Okay, so then what we're going to do here is we're going to look. So our Bohr diagram here, each of these rings represents the energy levels. So energy level 1, taking a look at our electron configuration, how many electrons do we have on energy level 1? Just 2, because the only thing on energy level 1 is our 1s. So on this first ring, we're going to draw 2 electrons, and we're going to label them 1s. Next, we're going to move on to our second energy ring. So on energy level 2, what do we have on energy level 2? 2s2. We've got 2s2. Anything else? 2p6. So we're going to have a total of 8 electrons on this ring. I don't care if you spread them out, if you group them together, it does not matter. So you can have them all next to each other, you can spread them evenly throughout the ring, I don't care. You totally could, yeah. I don't care. So then when you label them, how many 2s's did we have? 2. So 2 of these electrons are going to get the label 2s. And then the other 6 are going to get the label of what? 2p. Okay. Then we take a look, energy level 3. What do we have on energy level 3? 3s2 and 3p1. So we'll have 3 electrons. Okay, and then what are we going to label them? 3s 3s, 3p. And then that's it. Okay, so all we're doing is just matching up and drawing the electron on their corresponding energy level, which is told to you by the big number in front. Yes, question? So, next it says circle the highest energy electron. So, what was the last thing we wrote? 3p1. So, what's our highest energy electrons? Our 3p1. So, we're just going to circle this 3p. And then it says box the valence electrons. What are the valence electrons? Our outermost. So, which ones are those? Yep. Anything on our third energy level, so our 3s2 and our 3p1. So you can box them individually, or if you want, if you have them grouped close to each other, you can just box all of them like that. Okay. So then how many valence electrons do we have? 3. Which means, what is the most likely ion for aluminum? Al what? Plus 3. Because did we lose or gain? Good. Lose 3. So what's the new electron configuration going to be? So if we're losing 3, it'd be 1s2, 2s2, 2p6. Because we're losing all of our valence electrons, and we said that our valence electrons are the 3s2 and 3p1, so all of those will be gone. All right, so would this be larger or smaller? Smaller. And then what noble gas is it going to be isoelectronic with? Neon. Okay. Questions about our Bohr diagram? I think it's fairly simple. You just have to recognize that your big number is telling you what energy level, and then you have to remember to label them. If you don't label them, you're going to lose points. Okay? All right, so I'm going to have you do bromine on your own. So go ahead, pause the video, and then come back to check your answer. All right, so here is the answer. So your electron configuration should have been 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Your orbital diagram should have gone out to 4p. Everything before 4p is full. 5 orbitals, so 5 boxes for 3d, okay? And then you should have 5 arrows in your 4p. Okay, so whenever you fill in your Bohr diagram, you should have 2 electrons on your first energy level, 8 on your second, 18 on your third, and then 7 on the fourth. Now, I heard a lot of people saying, I thought that you could only have 8 electrons on an energy level. And this is what middle school teaches you. Middle school teaches you like a half-truth, okay? So they teach you that you can only have 8 electrons per energy level, when the reality is you can only have a max of 8 valence electrons on an energy level, okay? So when we look at this, our 3D electrons, they start filling after we've started our 4s, which means that we already have electrons on the 4th energy level before we go back and start putting them on the 3rd again, which means that these 10 3D electrons can never be valence electrons, because at that point we already have some on the 4th energy level, and so our 4s electrons are the valence. And so that doesn't break the rule of having only 8 valence electrons at a time, because these, whenever we go back and add the D, they're no longer valence. So you can have more than 8 electrons per energy level, as long as it's not energy level 1. Energy level 1 can only have a max of 2. Every other level can have more than 2. Okay? Level 3 can have 18. Level 4 can have as many as 32. Okay? Because level 4 is when we introduce the F sublevel. Now, we're never going to make you draw a Bohr diagram with the F sublevel, okay? This is about as big as we're going to get. We probably won't make you draw an orbital diagram with the F, but we will make you do an electron configure, like write out the full electron configuration with an F. Okay, yes. 32, yeah. So at that point, we would have some on the next energy level, and that's what we would look at. So if we have, so like this 4th energy level, if we've got 30 electrons on this 4th energy level, that means at that point we've already added some to the 5th energy level. So we would use our 5th energy level to determine valence electrons. Okay, any other questions? Okay, so our circle the highest energy, those were our 4p, that's what we wrote last. Box the valence, that's whatever is on our 4th energy level. We should have 7 valence electrons. And since we have 7 valence electrons, bromine is going to form an ion of Br minus 1, because it's going to want to gain 1 electron to get up to 8 valence. Meaning the new electron configuration, instead of it being 4p5, it's 4p6. We're going to have a larger, it's going to be larger. And then the noble gas it's isoelectronic with is krypton. Questions? Yes. It gained an electron, so by gaining it just gets bigger. Okay, so we're going to skip this Bohr diagram, and we're going to go on to writing with the F, okay? This may be as far as we get today, but I'm going to continue this video and finish out the rest of this section of notes, but we will finish it in class next time, okay? But those of y'all watching from home, I will go through and finish the rest of this section. All right, so let's talk about how we're going to include the F block, okay? So whenever we write the F block, our periodic table here shows you where it goes. This is our F block. It shows you that it goes in between your 6s and your 5d. So all you would do is you would have 6s2, 4f14, and then continue on with your 5d. That's how you write the F. Okay? So this one asks us to do tungsten. What's tungsten? W, so that's right here. Okay? So W, tungsten, is in what spot? What block? So it's going to be 5D what? 5D4. So 5D4. So that means that we're going to get to 6s2. So everything's going to stay normal until we get to 6s2. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. Now we're at 6s2. I know, that was fast. So we've filled all the way out to 6s2. That's the same as we've always done it. Okay, nothing different there, just a lot. And then we're going to go and do our F. So is tungsten in the F block? No. It's after, so we're going to have a full F block. What is that going to be? What F? 4F. So it's 4F what? 14. So it's going to be 4F14. It's our, so this starts with 4F. So we had 1S, 2P, 3D, 4F. Okay, so this is 4F. And if you forget, if you forget that F has 7 orbitals, you can count the elements across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 4F14. And then we said tungsten was 5D what? 5D4. Y'all, shh. Huh? Well, 5F14 is the next one. That's your actinides. No. So no, so this one here, so our lanthanides, that's 57. That goes in between 56 and 71. Our actinides starts 89. That's the one in between. So our lanthanides go in on period 6. Our actinides go in period 7. Yeah. Okay. So next we've got platinum. And so we're going to find platinum on our periodic table. Platinum is right here. So that is in our 5D, 1, 2, 3, 4, 5, 6, 7, 8 position. So we're going to fill out everything, and then 5D8 is where we're going to stop. So that would look like 1S2, 2S2, 2P6, 3S2, 3P6, 4S2, 3D10, 4P6, 5S2, 4D10, 5P6, we're back to 6S2, and after 6S2 is our 4F, so 4F14, 5D8. Okay, now that's a lot to go through. So instead, what we have is we give y'all a shortcut. So this is our abbreviated or noble gas electron configuration. It's a shortcut. So like I said before, all of these atoms want to be like a noble gas. So what we can do is we can choose the noble gas before our element. And by writing that in brackets, what we're basically saying is everything up to the electron configuration that that noble gas has is included just by writing that. And then we just continue after. So platinum. Looking at platinum, the noble gas before platinum is xenon. So what we would do is we would write xenon in brackets. And xenon is in our 5p6 position. So that means 1s2 all the way through 5p6 is included just by writing xenon in brackets. So after the 5p6 comes our 6s2, so that's where we're going to start. 6s2, and then we'll write our 4f14 and our 5d8. Now that's a lot easier writing this than all of that. Okay, so now looking at antimony. Antimony, the noble gas before antimony is krypton, so we'd put krypton in brackets. Krypton is in the 4p6 position, which means we'd start at 5s2. And then we'd go, so after 5s2, we would hit 4d10. And then antimony is in our 5p3 position. Okay, I want you to try mercury. So pause the video and then come back whenever you've got that done. Alright, so for mercury, it's going to be the noble gas before mercury is xenon. So then again, we'd start at 6s2. Then we'd have 4f14. And then Mercury is in the 5d10 position. And then that's it. So that's a lot easier than having to write this out each and every time. However, you have to be careful because on your assessment, we will ask you to write out the full electron configuration, and we'll ask you to write out the noble gas. So make sure that you are writing them appropriately. If it doesn't say noble gas, then we want you to write out the full thing. All right, so then we're going to talk about identifying elements using that electron configuration. So when given the electron configuration, figuring out what element you have. This is arguably one of the easiest because all you have to do is look at the last one. So the last thing we wrote is 3p3. So we go to our periodic table, find our 3p, so this would be our 3p. So what's in our 3p3 position? 1, 2, 3. Well, that's phosphorus. So this element is phosphorus. Looking at B, the last thing we wrote, 4d7. So going back to our periodic table, 4d would be down here. So 4d7 would be 1, 2, 3, 4, 5, 6, 7. This here, which is rhodium. Okay, so I want you to do the next two and then come back and check your answer. Alright, so the answers for C and D are bismuth and borium. Bismuth is in that 6p3 position, and borium is in that 6d5 position. Okay, so on to our last page. And we're going to talk about exceptions. So there are some exceptions for these electron configurations, okay? So elements whose electron configuration is in the D block, okay, they do not like to have D4 or D9, where we have 4 out of 5 orbitals with 1 valence electron, or 1 electron that is not paired out of the 5, because these are super unstable. So instead what happens is, because these are higher energy than our S, this D block is going to steal an electron from our S sublevel so that we are more stable in our higher energy amount D. Okay, so we're going to write the abbreviated electron configuration for chromium. So chromium is atomic number 24. It's in the 3d4 position. Okay, so it ends in that D4. So we want our abbreviated, okay, so that means the noble gas before chromium is argon. So in our brackets, we're going to have argon. And then we start with 4s. And writing it normally, it would look like 4s2, 3d4. But that's not what it is. That's unstable. We don't like that. So what it does is it becomes 4s1, 3d5. So then the orbital diagram for this, we would have our 1s, 2s, 2p, 3s, 3p, 4s, 3d. Okay. We know that everything up to here is going to be full, so we can go ahead and fill in here, okay? But now this is 4s1 and 3d5. So we're only going to have 1 electron in this 4s. And then we're going to go and put 1 electron in each of the boxes for 3d. because this is more stable than 4s2 3d4. Okay, so I want you to try copper and then come back and check your answer. All right, so copper, if you noticed, was in the 3d9 position. So d9 was one of our exceptions, meaning instead of having 4s2 3d9, it's going to be 4s1 3d10. So whenever we draw our orbital diagram, we would have one arrow in our 4s, and then our 3D would have 2 in both, or 2 in all of our orbitals. So 10 electrons in the 3D. All right. So last thing we're going to talk about is what about some metals that have more than one charge? So many of our D block and P block metals can actually have more than one charge, and it all depends on which electrons and how many electrons are being lost. So for example, our P block metals can lose just the valence P electrons, or they can lose both their S and P valence electrons, meaning that these elements have two possible charges for these ions. So one of these examples is bismuth, okay? So bismuth, we're going to write out the electron configuration for bismuth. So bismuth is in the 6p3 position, and this is just the abbreviated. So the noble gas before bismuth is xenon. And then we start with 6s2, 4f14, 5d10, 6p3. Okay, so if our ion is only going to lose the valence p electrons, what would be the charge? Well, how many valence electrons do we have in our p sublevel? We have 3. So our bismuth ion would be losing 3 electrons, so it would have a charge of +3. Okay? But what happens if it loses both the S and the P? So how many valence electrons does this bismuth have? Well, look at our S. So there's 2, and then 3 in our P. So it has a total of 5, meaning that bismuth could also have a charge of +5. So sometimes bismuth only really has energy, or only has the ability to lose just its P electrons. It can't find elements to give the other electrons to, or it just doesn't have the energy, okay? So sometimes it's going to lose just the P and have a charge of +3, but other times it can lose all 5, and so it'll have a charge of +5, okay? So go ahead and do the same thing for tin, and then come back and check your answer. All right, so tin is in the 5p2 position, so the noble gas before tin is krypton, so we'd have krypton, and then 5s2, 4d10, 5p2. If it were to lose just the valence p electrons, there's only 2 of them, so tin would have a charge of +2, whereas if it were to lose the S and the P, it would lose the 2 from the S and the 2 from the P, resulting in a charge of +4. So these only apply for the for our metals that are in our D and our P block, and most of the time we're really only going to have y'all do this for our elements that are in the P block. Alright, so if you have any questions whatsoever, please come see one of us for tutorials. We're more than happy to help you. Otherwise, make sure you study, and we'll see you next time. Bye-bye.